This video is an introduction to the concept of inverse functions, and we'll start with the following problem. You took a week off in Florida, and you turn the TV on and look at the weather for the next few days, Monday to Thursday, and this is what they tell you. So you're kind of happy. It's mostly sunny except for one day, but then you've got all these temperatures in Fahrenheit, and you actually understand what temperature in Celsius is, but in Fahrenheit you have you don't know if 85 is warm or not, or if 70 is actually pretty cold. So what kind of clothes are you going to wear on those days? So you start to do a little bit of research online, and then you find that, or maybe you go back to your problems from this course, and you realize, oh, the teacher gave us at some point a relationship between temperature in Fahrenheit and Celsius, and there was actually a problem like that in the exercises where I gave you the actual relationship. This is correct. F is in temperature in Fahrenheit is 9/5 of the temperature in Celsius plus 32. This is absolutely true. And then you're like, okay, I'm pretty solid on algebra. So what I'll do is for Monday, I'll just replace temperature in Fahrenheit by 75 and then solve the equation for C. Okay, you're like, okay, I can do this. So 75 minus 32 is 43, and then this is 9/5 of C, and then you multiply 43 by 9/5 of 43 by 5/9, and that's going to give you your temperature in Celsius, and ultimately it's 28.8. Repeated is C, so that's your temperature in Celsius. And you realize you have to do this for Tuesday, Thursday, Wednesday, and Thursday. And then you think, well, actually, you know what? All these steps that I did here, I'm going to do the exact same steps. So why not actually do it with the formula for once and for all, and then just plug in my values in the formula afterwards? So we're going to solve actually the equation for C. So this way we won't have to repeat all those steps. It's going to be done once and for all. So we're going to do what? F minus 32 is 9/5 of C, and then we multiply by 5/9 on the other side, F minus 32, and we get C. And actually I'm going to write it the other way around like that. Okay. So we have two equations here, and with this I'm able to recover, temperature on Tuesday. That's easy. I could just plug in replace F by 85, subtract 32. I calculate this, it gives me 29.4 repeated, and then you can do the same for Wednesday. This is actually 70 here, so I should write down. That's going to give you 21.1 repeated degrees Celsius each time, and over here for Thursday you can do the same thing, so you get the idea. And that's 26. The numbers that's really important here. The point is that now, instead of plugging in Celsius into my formula, I'm plugging in Fahrenheit and immediately getting Celsius. So what has happened here? So initially we had an equation where everything's solved for F. So here we've got F here is a function of C. Okay, give me C, I'll give you F. Okay. But what actually we wanted is to start with an input in Fahrenheit and get the output in Celsius. So this is why when we solve for C, this is what this gives us. Now we've got that C is a function of F. And that's really what we wanted in the first place. Okay. So this was actually possible initially, like to take the initial equation and solve for C, because we're dealing with a one-to-one function. Okay. In other words, if you've got two variables and you can solve the equation for either variables, you have two functions where and if it's like we have here, f and c. In one case, f is a function of c. In the other case, c is a function of f. So in one case, the input is c, the output is f, and then it's kind of backwards. The input is f, the output is c. And that's really possible because we have got a one-to-one function. In other words, initially, when you're given c is a function of f, but it's a one-to-one function because there are no two temperatures in Celsius that are associated to the same temperature in Fahrenheit. Okay, if that were the case, we don't have a one-to-one function. We have one-to-one when all points in the input are connected to a single point in a unique point in the output, like this. So temperature 3 would be associated to F3, that's a temperature in Fahrenheit. Okay, and they're all different. And this way you can actually create a new function by just changing the order of the arrows, the sign of the arrows, and creating therefore a function where c is a function of f, which is what we have in our last equation, right? We've got c is a function of f. So by solving for c, we've reverted the sign of the arrows. And that's basically the inverse function of the initial function we had before. So using this diagram, let's take another look at our problem. So we had essentially the original function. Okay, and I'm going to draw a function machine. Okay, you feed it Celsius and it outputs Fahrenheit, because the relationship was written in the form f of c is 9/5 of c plus 32. Okay, so for example, if you feed it 26.6 repeated Celsius, okay, the output is 80 Fahrenheit. Okay, that's a fact. Now our new function, you can call it G. You actually feed it Fahrenheit and then it outputs Celsius. And it's this one. Okay, so it outputs Celsius. So you can feed it Fahrenheit and it outputs Celsius. If you feed it 80 Celsius, of course, it's going to output 26.6 repeated. If you feed it 80 Fahrenheit, it's going to output 26.6 repeated Celsius, exactly. So we actually see that the domain of our original function and its range are not inverted. So the domain of the new function is actually the range of the previous one, and its output is actually the domain of the initial function. So these are equal and these are equal. Okay. And let's take another look using the notation. So we also have, so maybe actually, you know what? I'm going to write down what I just said here. So the domain of the new function is the range of the old function, and the range of the new function is the domain of the old function. Now this new function is what we'd like to call the inverse of the initial one. Okay, so the domain, normally we're going to say the domain of the inverse is the range of the initial function. The range of the inverse is the domain of the initial function. And also using this the function notation we have here, if I do g of f of 26.6 repeated, now f of 26.6 repeated, that's 80, right? So if you feed 26.6 into the function machine f, it outputs 80. But then if you feed 80 into g, into the inverse function, okay, it outputs 26.6 repeated. So nothing has changed. What we actually have here is what comes out of composing the two functions together. We could also verify that if I do f of g of 80, okay, g of 80 is 26.6 Celsius, and 26.6 Celsius, okay, applying F to that, we're going to get temperature in Fahrenheit, so we get 80. So again, if it's 80 here, it's 80 there. So in general, what you have is that G of f of x is just x itself. So G and F compensate for each other. The one undoes what the other did, okay? And we've got this. This is true for all. So initially, so this one is, I'm running out of space here. This is true. Actually, you know what? I'm not out of space. I can just slide down like this. So this is for all x in the domain of f. And this is for all x in the domain of g, which is the same as the range of f. It's kind of the same principle as saying if you do times 2, okay, and then you divide by 2, those are inverse operations, okay? So if you do take a number, 7, you multiply by 2 and you divide by 2 afterwards, you're going to get back the same number. So it's the same idea with functions. So sometimes we illustrate this with a little diagram, okay? If you've got x, you apply f, okay? You're going to get y, which is the image of f, or f of x, okay? Now if you apply the inverse function, and we're going to introduce a little notation here, we actually write it as f and subscript minus 1. It's not a power, okay? So maybe I should write this immediately. This is not a power. This is not an exponent. This is not an exponent. So f minus 1 is not a power of f or whatsoever, okay? Okay, this is just a notation, okay, of the inverse. It is how we write the inverse function of f. Okay, so if you do f and then you take what came out of f you with input x and you apply f minus 1 to that, you're going to get back x again. So in other words, if you do f of x and then you take the inverse of f of x, you're going to get back. So the inverse is exactly what g was in the previous problem. You're going to get back x. If you do f of f inverse, you're going to get back x. And you see this, if you take any number here, apply f minus 1 to that, okay, and do f of that, you're going to get back to where you started. Okay, so you can also loop like this. This was the last equation showing. Okay, and that's true for all x in the domain of f for the first one, and all x in the range of f or in the domain of the inverse for the second one. Maybe if you're not convinced still, you can replace, if that makes more sense to you, you can put y there if you want. Okay, so this would be for x in the domain of f, and this is for y in the range of f, which is the same as the domain of f inverse. Okay, but usually whether we put y or x, it doesn't matter, right? It's just a variable, so we can just rename that y x, and then this is how we get f minus 1 of x is x. So this is what actually an inverse function is. It's a function that satisfies these two equations, okay? And maybe I'd like to add one more thing to the to my little warning here. So when you write f minus 1 of x, you can't write 1 over f of x. Okay, that's not it at all. Okay, so f minus 1 of x, or we usually say the inverse of f applied to x, is it's just a notation on its own. So it's really like a g. Okay, it's a symbol. Okay, f minus 1 is just one unique symbol. You cannot start playing around with it. And why do we write f minus 1? It's analog to a minus 1 times a. So it's analog actually to something we have for exponents, where if you do a minus 1 times a, you're going to get back 1. So here the idea, so you get the in some way the neutral element for multiplication. So when you do f minus 1 of f of x, you get x. So you get x is the function that's not changing x. So if you've got a function that's h of x, which is x, okay, it's not changing the input. Okay, it's the function that's the identity function in some way. Okay, so so if you compose, for example, f with h, okay, nothing has changed. It's just f of x. So it's the same idea with the 1. If you do 2 times 1, it's not changing anything. You're just going to get 2. So that's why we use the same notation with the that we have for exponents for functions. It's just to remind us that the inverse is basically undoes what f actually did.